This program has been made possible by a grant from the UCF Office of Research and Commercialization.
The UCF Office of Research and Commercialization is committed to moving the discoveries of our faculty and students from ideas to innovation to realization. By moving research from the laboratory to the private sector, we are helping to diversify Florida's economy and helping to bring high-paying jobs to our state. This program presents some examples of our research and our efforts to transition this research to the private sector.
Hello and welcome to Zenith. I'm your host, Ed Hyland, and today we're going to learn from the burn and wrap up everything with a string. Well, confused? You won't be. We'll get to a discussion of the string theory later in the program. But first, the burn is research into fire, specifically arson fires, and the forensics needed to figure out how they were set. A University of Central Florida professor working with the National Center for Forensic Science has come up with some new math that may make the arson equation more accurate than ever before. It all begins by torching a test chamber.
We got the back propped open about 4 inches.
We took 4 containers, storage containers. We built them out on the inside like a standard apartment, drywall, carpeting, furnishings. We made each of the 4 identical as best we could.
Look at the couch. We're approaching
1,000 degrees at the couch and 440
couches at 1,000.
440 at the ceiling.
One of the containers was burnt without the use of an ignitable liquid to help start the fire, and 3 of the containers were burnt with ignitable liquids to help start the fire.
Okay, we've got it rocking. All right, look at it go. We're going.
We set the fires with or without the ignitable liquid, let them engulf the interior of the containers, and then the people from the fire college went in and knocked the fire down.
Have to do a little bit more air at that front door.
In a case where you have someone who sets a fire, there will be traces left of the ignitable liquid in many cases. However, the amount of ignitable liquid that's there will vary. In addition, when you have a fire in a room, the materials in the room, the carpet, wood, everything, under the intense heat will start to break down. And when it breaks down, it will make other chemicals that are very similar to, if not identical to, in many cases, the chemicals that would be used in the ignitable liquid that started the fire. And the methodology that we have used is to take multiple samples from the scene. Each sample will have a different level of contribution from that fingerprint from the ignitable liquid. We put all of that data together, and it's easier to analyze that data and identify that fingerprint if you have all of the data rather than just the one sample, because now you can look for the commonality in all of the data sets. And that's what we do, and it's a mathematical process that's called target factor analysis, where we analyze all of the samples and we scan that data against a database of ignitable liquids, and we identify the ones that are the most similar.
Well, our job with arson investigation doesn't get any easier because we have so many new products in the market that are producing so many different chemical compositions. So when we do an analysis, we have to try to isolate as best we can an accelerant if it was used in a fire. So the methodology that UCF is using, we're very hopeful is going to help us with that process.
In the year that preceded those tests, we've done a large number of tests in the laboratory. And in those tests, we would use a metal container, a small metal container, with, say, carpet padding, woods, that sort of thing, and a small amount of ignitable liquid, and burn multiple samples, and then put together a data set similar to what we took out of those larger containers. And we've used the mathematical process, we've refined it, it works great on the laboratory burns, and we're really looking forward to getting the results out of the larger scale burns.
It's hoped Professor Sigmund's research will help establish a gold standard for arson investigations. The grant is budgeted for at least one more and perhaps two more burns in 2010. Now, what about that reference I made earlier in the program to wrapping up everything with a string? Well, when we come back, an interview with an expert on string theory, a unique concept that might lead us to a better understanding of where our existence began. Details coming up. Most of us view the world as a three-dimensional place with width and length and depth. But math and science have long theorized that other dimensions might exist. And according to physics professor Tristan Hoopsch, now lecturing at UCF, the more dimensions we have, the more we can learn about ourselves.
Well, the theory of everything is, as the name would suggest, a theory that would explain everything, but that's a little bit of a misnomer. The theory of everything is applied to what we talk about in what used to be called particle physics, variably then high energy physics. And these are all somewhat inaccurate statements because how high is high energy physics and exactly what particle do we imply by saying particle physics. But at any rate, it's, I would like to say, the fundamental physics, the physics of fundamental interactions and the fundamental building blocks of nature. And so the theory of everything would be a theory that describes everything pertaining to those fundamental building blocks. So we know for quite some time now that matter, such as this table, our clothes and our bodies, are made of atoms. Atoms in turn are made of electrons orbiting some nuclei. Nuclei can be broken down into protons and neutrons. All of these are just some names for particles, right? And then this theory of everything would have to be a theory that describes which exactly building blocks do we need, how do they bind together, how do they interact, how do they make up what we call a table or what we call a nice suit or what we call the plant behind you, and how do those function.
Now give us an idea of how the string theory fits into the theory of everything. Is the string theory the theory of everything?
Well, theory of everything is a goal. In all of physics, we do modeling. When we talk about Bob moving on a spring, you must have seen something like that way back in school.
Of course.
Right. And this is just a model. We describe the bead, the bob that is bobbing up and down, we describe it as a point-like particle. Because for the purposes of it wobbling up and down, it's really irrelevant whether it is spherical or pyramid-shaped or whatever. So much like that, when we try to describe interactions like how does light that is shining out of those light bulbs, how does it hit my skin and then reflect, and then when it reflects off of my jacket it comes out gray, when it reflects off of my shirt it comes out purple. So how does that exactly happen? We make a model, a mathematical description, which helps us compute, which helps us predict that when light shines on my shirt it is going to come off as purple, and when it shines on this part of my tie, it is going to come off white. So we have these models, and in a attempt to describe everything that we know of, which includes, I'm sure this has happened to all of us, you wake up in the morning and you realize there is gravity, and I am very heavy today.
Especially on Mondays.
Yes, that tends to happen. And then you look into the mirror and you realize I haven't disintegrated yet. My atoms are quite still robust. And we've learned to associate quantum mechanics with that robustness of nature, with the fact that atoms don't disintegrate. So quantum mechanics and gravity are two of the things that have to be inside this theory of everything. And there is a very simple way of understanding why these two don't want to play well together. I'm sure, at least in Star Trek or someplace like that, you've heard of Heisenberg indeterminacy relations or uncertainty relations. It essentially tells you that a particle cannot be told infinitely precisely where it is and how fast it moves. We cannot measure it infinitely precisely, and it's not because our measurement apparatus is somehow faulty. It's because this is the inherent nature of nature. For no object can you determine infinitely precisely where it is and how fast it moves. On the other hand, gravity is described very aptly and very accurately by this theory, which has this simple principle. The presence of matter curves space-time. It tells light how to bend around, it tells other particles how to move around. And unfortunately, when the presence of a particle curves space-time, then you can tell this is where the curvature sits, this is where the particle is. So relativity, which is our description of gravity, wants us to be able to say exactly where the particle is and how fast it moves. So those two clash. Enter string theory. If the objects are not point-like particles, but little strings, like little loops like this that vibrate, oscillate, they're kind of fuzzy in that sense, then the uncertainty relations cannot really tell exactly where the string is because it keeps on vibrating and wobbling and moving. Yet the center of mass of that string is at a very well-defined position, which is what the theory of gravity wants. So this is how these two, quantum mechanics and general relativity, which we use to describe gravity, how they get reconciled in string theory. Now, mind you, it doesn't mean that string theory is definitely the only possible such theory, but it definitely says that it can do it.
So let me try and back up a little bit, because you're talking about basically a framework for the entire universe.
Yes.
Now, so we have this framework, and if the string theory is the correct one, or you say there's some alternatives, how do we go about proving? How do we go about really confirming that the theory is in fact fact?
Well, one of the proofs is right there. We know that both quantum mechanics and relativity, gravity, have to coexist. And the only way in which we know how to do that, and also include other things that we know of, such as weak interactions, strong interactions that held the nuclei together. Weak interactions are interactions which help something called beta decay, which is daily measured, and it's in fact one of the things that contributes to how the sun shines the way it shines and why it shines at the rate that it does shine and provide life on Earth. So these are very important things, actually, not academic, irrelevant, discussions. So all these things do fit into string theory. Now, there are some other suggestions how we might reconcile quantum and gravity. But those attempts do not include any of these other facts of nature. So I would say that string theory definitely wins out so far. Now, it may happen that someday soon one of our current students is going to be that bright mind that will come up with some totally different way of looking at things and teaching us how it is to be done much better and much easier in some way that can be more readily experimentally checked, which is what you were after. But right now, this is what we've got.
Let's talk a little bit more about, we're talking about string theory and a dynamic shape, I guess you would say, for these strings. And in doing some of the research and getting a little assistance in this, the discussion of the Calabi-Yau manifolds came up. Now this is a shape. This is different than strings, so kind of build on that one for me.
Well, strings, or string theory, the theory of how strings move as opposed to point particles, has certain restrictions that point particle theory does not have. So what we have been practicing up to about 1974 or so, point particle theory exclusively, assuming that every object that we deal with in laboratories or so ultimately can be broken down to building blocks that are point-like. The simplest possible assumption, right? Well, for all those theories, there are no particular restrictions of the type that emerge when you assume that, now this object that I call the electron, or the object that I call a proton, or whichever other of these particles, is no longer a point-like object, but a little loop of stuff. And then these loops interact, and they interact in a very different way than point-like objects will interact. Just try it. Two marbles hitting each other, you can pretty much see how they're going to, what they're going to do. Now take two wobbly objects and smash them. They're going to interact in a very different way, right? So the mathematics of it gets much more complicated, But the bottom line is that there are certain restrictions in these interactions of strings which do not exist for point particles, and they predict that space-time, so space plus one time, is a total of 10-dimensional. Oops, except we don't live in 9-dimensional space plus 1-dimensional time. So you have to figure out how to make sense of those extra dimensions. So if I can borrow your sheet of paper here for a second, you would agree with me that this sheet is 2-dimensional, right? You can move that way and this way. Well, imagine I now do a little parlor trick here. I'm going to roll this up into a cylinder. You will still say that this is 2-dimensional, right? Because you can easily picture that you can move this way and you can move that way. Well, imagine me now rolling this up tighter and tighter and tighter, more so than I can do with a piece of paper, but to a point where it becomes a very, very thin straw. At some point, you're going to stop saying that this is 2-dimensional and saying, this is obviously 1-dimensional line, right? So it may well happen that the space that we live in has 3 dimensions, that way, and that way, which are large compared to our bodies, compared to our ability to move and manipulate objects, kick marbles and those particles that are supposed to be kicked around in the LHC sometime soon, but we don't have enough energy, or we don't have enough ability for some reason or another, and there are different kinds of proposals which would explain that, to move into that other dimension. So in my simile here with a little rolled up piece of paper, you see, if you think about it, you drove into work, right?
Sure.
You know that when you turn around the curve,
Sure.
you have to work hard to stay on that curve, right?
Okay.
So imagine if this curve is becoming much, much thinner, much smaller. You'd have to work a lot to stay on the curve, right? So the basic idea is that the tighter that extra dimension, in this case this sideways dimension on the sheet of paper, the tighter it is, the more energy the particle needs in order to move that way. And so if it doesn't have that much energy, it cannot move in the other direction. It can only move in this big direction because it doesn't take any energy to move in that direction, right? So that's the basic idea, how it might well be possible that our space is really 9-dimensional, but 6 dimensions are teeny and they're kind of curled up like some funky roller coaster ride, which simply requires too much energy, and we cannot move in those directions. And the particular shapes and sizes, and it's called topology, that's the fancy word for it, that is used to describe those objects is called Calabi-Yau manifolds, in honor of Eugenio Calabi, who conjectured the existence of such things, and Xingtung Yau, who proved that such things do exist.
So we need to start digging down, so to speak, need to go deeper and deeper. Wouldn't it take a tremendous amount of energy to get to that level where you'd actually be able to see some of what you've just described?
Absolutely it does. And the way we've been doing experiments the last century, I would say, it follows one of 2 types of paradigms. Experimental physics, in particle physics that we call, is essentially 2 kinds of experiments. I'm ashamed to say that in a century's time we haven't come up with anything better than this. But one experiment is simply, take one marble and take the other marble and smash them together and see what happens.
A collider.
Yes, a collider. And most of the time they're going to just bounce off like billiard balls. But once in a while something funny is going to happen, and you're going to see some new particles, or maybe these marbles are going to fall apart, and you're going to see shrapnels falling, flying every which way. But these are these colliding or smashing experiments, to use a funnier word. Maybe some of your audience would prefer that. The other type of experiments it has to do with processes that are extremely rare. So it would take me, most of the time, as I said, if you try to do an experiment, most of the time it doesn't happen. And every once in a blue moon, in a million or 100 million or 100,000 million times, it does happen. So there's a trick to that. Instead of doing the experiment with one object at a time, what you do is you find somewhere a defunct mine, lace up the walls with detectors, and then fill it up with water. Water is cheap, it does have matter in it, and it turns out that the type of experiments, it ends up being called the proton decay experiments, but that's the first of that type of an experiment, fills up a huge mine, as it happens, the defunct gold mine in India, the first one, fills up with water, and then you just wait, because there are a huge number of particles inside that amount of water. And even though the probability for any one of them to undergo this process is extremely teeny, it's to wait for that particle on the average to undergo this process would take more than the lifetime of the universe. But you have so many particles in this whole body that would produce some effect somewhere down the line. So we wait. Unfortunately, the waiting experiment only gives you a lower bound, because all you can say is that up to now it hasn't happened. And then you wait a little longer, so that bound gets pushed up and up and up in, in a certain frame of reference. But you don't know over here. In principle, that bound could be pushed arbitrarily far up. So this is what I would like our fellow experimentalists, obviously I'm a theorist here, what I would like our fellow experimentalists to come up with, a third kind of experiment in particle physics that would provide the complementary bound, the complementary information. We need to come up with a new way of making experiments. Because if we're going to do the same experiments, colliding experiments, the LHC is already, I don't know, 15 miles in radius or something. It's humongous.
The one in Switzerland, you're saying?
Right.
Yes.
Which is supposed to be running soon, let's hope, knock on wood. But what are we going to do after that? What, make a collider that runs around the Earth, around the Moon? Who's going to foot that bill? We cannot do that. It's impossible. We have to come up with a better way of doing experiments. And, well, the waiting experiments are radically different, and they're not all that expensive, and you definitely don't have to scale them up that way, but we need another experimentalist idea. It's not that I'm passing the buck on my buddies. I'll be happy to come up with such a thing, and, please give me the Nobel Prize for that.
Okay, well, when you do that, we'd love to have you come back and talk about it.
Absolutely.
Let's go back a little bit from the theory part to the practical part here, in the sense that, not that it's not practical, but the practical side of students, folks like yourself, people who want to get into it and perhaps find some other means of measuring. What should students be doing to prepare themselves to get ready to jump into all of this?
I'm afraid the real answer to that is about 25 centuries old, which is there is no royal road to geometry set to a king.
Study,
but
study, study.
Absolutely. Unfortunately or fortunately, look at it however you want to. It's fortunate in my opinion because it helps all different kinds of people communicate. The language of science is mathematics. I know that math can be a very scary subject for a lot of young students, but it definitely is the best way to try to communicate to each other. We can argue, if I meet my colleague from China, we can argue, as they say, till the cows come home over this or that, or whether the concept is so and such. But when we calculate something, and he gets a square root of 2 and I get a square root of 2, hey, we're okay. It doesn't matter whether you call it blue and I call it red. We got the same result, and that's what matters. So when the math, which supports all these theories that we have, when the math agrees, that's the bottom line check. And so I would definitely recommend students to warm up to mathematics. And after a while, it's kind of like bicycle riding. When you're a kid and you're trying to ride that bicycle, you're going to fall down very many times. You're going to skin your knees, you're going to perhaps even get a bloody nose. But eventually when you learn how to ride the bike, you're going to know how to ride the bike for the rest of your life. And you're going to be wondering, how come other people don't? That's exactly what happens with math.
Well, like the rest of us, students often need some type of incentive, and certainly on the high school level, maybe even younger than that, and on the college level, there would seem to be a need for theoretical groups. How important is that particular application to really encouraging the best and the brightest to get into this research field?
I think it's extremely important, not just because I'm a mathematical physicist, but really I have become a mathematical physicist because it's something that I heard, in my inner voice or so, that this is how nature can be explored, and I was curious. And I'm pretty sure that there are lots of other young people around who do have that same curiosity. So we need to encourage them. There is no better way to encourage somebody than to show them how you do it yourself. And guess what? If you don't have such mathematical physics groups around here, then all those students that are coming to this campus are not going to see how it's being done. They will have to rely on whatever they can perhaps see on the TV or whatever they read in the Scientific American, but it's not going to be the same interaction as you can get when you're face-to-face to a student and they ask a question, and every now and then there's going to be a question that even a professor who has taught, like I have for about a quarter of a century, you get like, where did that come from? That's a very good question. And it sort of, brings that pause to yourself, and the student sees that. They see that you actually had to think about it. They see that, first of all, there are no stupid questions, that sometimes even a completely uninitiated student can, hit it upon the nail. And then you see how that process develops, where they've asked a question. Now you obviously have a good basis of previous knowledge, and you're getting to answer to that question. You're building that answer. It's not something that you've read in a book and you just, oh yeah, in book so-and-so, page 59, there's the answer. But you actually had to create that answer. And that's what the students need to see. That something like that they will never see if they only read books, if they only watch TV. They need that one-to-one.
The new ideas and the new theories, maybe like the particles in the mind, they just pop up on occasion. You have to be there to monitor and capture them when they happen. Well, Tristan, thank you so much for coming by and joining us today.
Thank you very much for having me.
All right. Scientists say the Geneva Collider may prove or disprove the string theory, but they expect to wait many years, perhaps a lifetime, before they get conclusive answers. Our time, however, is running short, with just enough left for our Research Minute.
See, when we started the biomedical science research and education enterprise, we selected 4 major areas for emphasis: cancer, cardiovascular disease, neurodegenerative disease, and infectious disease. Why did we pick those 4? Those are the 4 major afflictions of human beings. So what our thing has been to build research teams working on each of these, so we will have a critical mass of people working on all those 4 areas. Cardiovascular, of course, includes obesity and diabetes, which are major risk factors of cardiovascular disease. All the faculty members have been funded from the most nationally competitive agency, the National Institutes of Health, and many of them, or most of them, have multiple grants. And that is amazing in a time when, in the history of this nation, this is the most super competitive period. And our faculty members competing with the best in the country.
To view Zenith on your computer, just go to ucf.tv and click on Zenith under our Programs tab. The goal of research is to better understand the world around us. Our goal is to be a window to that world. For Zenith, I'm Ed Highland. Thanks for joining us.